for the introduction. Hello, everyone. Hope you all are doing well and staying safe. Well, it's a Sunday morning for me here at around 9 o'clock, and I understand that we all are on different time zones, and probably most of you are already well into your Sunday, enjoying a late Sunday afternoon and early Sunday evening. And I really appreciate that you all joining this webinar on a Sunday afternoon. And so I will try my best to make this worth your time, honestly. Well, I think I'm going to stop my video because I find it a little distracting. Um, so digital rock analysis is of late is getting a lot of interest in not only within the geologists or petrophysicists, but well into the domain of reservoir engineering as well. Just imagine having a rock and that's been digitized and getting into your computer. So I'm not talking about just a photograph of the rock, but the rock, its texture, the structure, the minerals and the grain and the pores, everything that you digitize, whether it's in the form of a whole core or sidewall core or cuttings and into your computer. So that gives you an immense opportunity to play around and do whatever sensitivity you want to do for reservoir engineers. If he wants to pass through the pores, the connected pores, different fluids and how these fluids are behaving at different saturations, all these simulations he can do. For a geologist, if he wants to see the grain to how the grains and the pores are being disposed within the rock and what kind of cementing or materials are there, all these informations, it's now at his fingertips, and he can extract all these informations very quantitatively, actually, from this digital rock analysis. So it's not just some pretty pictures or good animations, but it's actually quantitative data that you can incorporate into your workflow. I am a petrophysicist. I've been in petrophysics for the last 13, 14 years. And before that, I was a well site geologist and doing, starting my career as a mud logger. So I incorporate multiple different data from multiple different sources and different scales in characterizing the rocks and coming up with a good, robust, useful solution in understanding the rock properties or the reservoir properties. So I find actually digital rock very interesting for me as a quantitative data that gives me a much better insight into the rocks, and particularly the rock and fluid behavior and etc. Right. So for our purpose here, I'm going to limit our discussion today for mainly two technologies. One is the CT scan, what you call this computed tomography, and the other one is the scanning electron microscope for imaging purpose. So we are not going to go deep into the technical nitty-gritty of all these, like how the image is acquired and all this, because that's not the objective of this presentation. The main objective of this presentation is to understand what digital rock can give you and how we can integrate that information with the rest of the other formation evaluation methods to come up with a proper characterization of the rocks, right? So that's the main objective. So CT, like you might be thinking about it, it's, yes, you're right. It's the same, the CT machine that you can find in a hospital. So there's the same CT machine we are using here. It's instead of human now, we are using the rocks to pass through it and actually generating very high resolution slices or of the thin section or the sections of the rock, and then combining them into come up with a three-dimensional image of the rock, right? So the CT is nothing but an X-ray, and it measures depending on the different rock properties. This X-ray get attenuated, and from that property, actually, you can capture the heterogeneity of the rock and does all the characters of the rock as well. So loosely, in that CTS attenuation is also a function of density and the photoelectric factor. The photoelectric factor is the lithology indicator. So these two, actually, you can calibrate it in our lab now, and then we can get a very robust and very accurate data on density and photoelectric absorption defining the rocks or the rock composition or the type of rocks at a very high scale, much higher than what we generally get from a wireline log kind of measurement. And the second one, when you go into much little bit deeper into that, we are going into the nanoscale or micrometer or nanometer scale. At that point, we use the SEM technology to characterize it. So SEM, it can be either in a two-dimensional, or when you stack those two-dimensional images over one another, and actually you can form a cube and to get into the three-dimensional mode. And at that point, either from the CT scan or from the SEM, both of these actually you can bring into your computer and characterize the rock, or you can play with that, or do all those different simulations that those I have already mentioned. Like the SEM, CT also has a very high resolution method that is called the microcity. So instead of the whole core rock, or you can actually cut a very thin pillar of the of a rock, which may be of a 2 or 3 millimeters diameter, or maybe even go smaller than that, and analyze that using the microcity measurement. So the source for the materials or the rocks could be all these different sources available for us, right? Whether it could be from the drilling cuttings, or a rotary sidewall cores, or a whole core. The whole core, it could be directly coming from the rig side, not extruded from the core sleeve, and you can actually get that core with the sleeves into our the CT machine, and actually we can still go ahead and measure the CT. We can do the CT scan of the whole core. Or if it's coming from another lab, generally as soon as the core arrived in the lab, then once they extrude it, they slab the core. So we can actually work from a slab core as well. Not necessarily it has to be always a whole core. So ideally, these are the three different ways or the source of the samples that we can analyze or digitize to get into our computer. So we are dealing with multiple scales, right? I mean, when you talk about the whole core, and the whole core is in meters or feet, and then from there, we scan the whole core and understand all the heterogeneity and the properties, and based on that, we actually decide where we can pick some plugs for further analysis. So once we do those plugs are generally either an inch or an inch and a half diameter, maybe 2 inch or 2.5 inch in length. So you see now we are going from meters or feet to inches, and then further we then, for our digital rock analysis, actually we take a very small chip of that core, that plug, and do the digital rock analysis on them. So we are now going into much smaller than even an inch, in looking into the nano or the micrometer scale. So it's a multiple scale of data that we are handling, and then we are looking into it, and then we are upscaling that to the again back to our whole core, or the or to a level where actually it's become more useful. So let's talk about the CT scan first, and then we'll go into the SEM analysis. So the CT scan, when we are doing it, we are measuring the CT scan into 0.3 millimeters resolution over the entire core. So it's a lot of data and a very high resolution in defining the rock and catching the heterogeneity of the rock, right? And at the same resolution, we are getting the density and the photoelectric absorption, and that's that's is a lithology indicator property of the CT scan. So we got these two with a very high resolution, and then at the same time also we are actually using our gamma ray measurement at a very high resolution over the core. So the gamma ray is not only just total gamma ray, but actually it also has the it's a spectral gamma ray. So it's basically potassium, uranium, and thorium. Now you have a full length of parameters, not only the density density and the PE, but as well as the gamma rays. That includes potassium, uranium, and thorium. So you can now actually define the rock in a much better way. So a geologist, when describing a core and trying to understand the whole heterogeneity or the texture of the rock and all and defining all these different phases, it may take days actually to get to a very good granularity or getting into very accurately. But once you have that core digitized and into your computer, you can do that in within a day or two. And actually it's with a much more accuracy because now you have all the data is well defined and digitized, right? So actually you can have a very continuous um, uh, textural log, which otherwise is not possible from a conventional core options. So when we combine this core along with our the gamma ray information of potassium, uranium, and thorium, and then we actually further define that we can actually compute all the at least the major mineralogical components, maybe the clay, sand, and the carbonates, and define the heterogeneity along, or the phases. And on that basis, actually using a machine learning approach, we can define on the or pick the core plug locations. Otherwise, a geologist or a petrophysicist would have picked those core plugs, looking at the core visually and trying to understand the heterogeneity and pick it up. But instead, here now, since it's a digitized, we are using those informations and using a machine learning approach in defining those phases. We are picking up these the plug locations. So ideally, you can think of it like if you are seeing a more or less a homogeneous section, then probably we'll limit the number of plugs that we want to cut there, and only maybe one or two. But whenever we are getting into a more heterogeneous rock, then we will take our the plug frequency higher, right? Maybe we need more rock samples to define that define the properties of that rock. So accordingly, you can actually optimize the core plug taking the option. You not necessarily, a lot of time people do like go at a uniform rate, like every 1 foot they want to cut a plug, but that not necessarily could be representative. One big advantage of this method is also that when you have the CT scan and you locate a plug location, actually before even cutting the plug, you can one can actually take a virtual look at it. So you can virtually extract the plug from the city data and look at it, how heterogeneous or homogeneous that is. So for example, now here, if you look at this plug has distinctly two different lithologies here, right? So now if you send this to a conventional core analysis lab, at that point, when they give you a porosity number, it'll give you one porosity number out of this plug. So it's actually representing two different lithologies. So that porosity is not actually representing the whole both these, but it's a kind of a mix of both these different lithologies, right? So when you look at through this image, or you understand that there is a heterogeneity within this plug, and then accordingly you can actually divide this, or maybe taking a section here or taking a section here and defining differently, and actually estimate the porosities from both these sections. And now, since if you remember, we talked about defining those different phases, and from the conventional city, or sorry, the whole core city measurement, this can be upscaled back to that, because all these different phases are already been defined there. And once we know the characteristics of within these two, then we can upscale back to the whole core analysis. So this data is quantitative. It's not just a qualitative understanding of the rocks, right? It gives you more accurate number or the pores or the other features that you are seeing. So for example, here now we are looking at some of the vuggy porosity or some dissolution, the pore structures within the rocks, and we are seeing some burrows or some matrix porosities. So all these can be quantified and getting into and giving you a more useful data that you can integrate back to your the workflow to characterize the reservoir. Similarly, for the geologists, they can group them into different texture-based classifications, and all these plugs, this is a density measurement variation. So you can see like higher colors indicating higher density or lower colors indicating lower density. So you can, one can actually see how heterogeneous or homogeneous these rocks are, or how you can texturally vary from one group to another group and identify them, and then actually create a continuous curve and defining those textures using this information. Similarly, we can take thin sections out of that and identify more in-depth mineralogy or other informations, and then identify those back to our the plug level and upscale it, and then from the plug level we can go back to our the whole core level. So this is how these things are integrated. So it's the whole core CT scan, then the plugs and the CT scan of the plug, and then maybe making thin sections out of that, and then identifying different properties there, and then upscaling back to the plug level, and then going back to the whole core level. This is just a flow chart showing you how these things are done. Once the plug is cut, this plug generally is of a diameter of maybe 1 inch or 1.5 inch. And then for digital rock, actually we don't need the whole plug. We just need a very small part of that, which is, we call it like an end trim. It's a very small chip out of that, cut from there. And then actually further you can divide that end frame into multiple, or at least two, broadly divide it into two sections. The one part you can conserve it, and the other part we can use it for further investigation. For example, like doing the SEM. And if you remember, I was talking about the microcity. That microcity pillar, we can create one here, which is in the scale of like a very small, right? It's in a 1 to 2 so 4 micrometer resolution here. And so depending on what kind of rock we are drilling with, for example, like if we are looking into some unconventional organic rich rocks, which pore size are very small or pore diameters are extremely small, maybe at that point a SEM or scanning electron microscope kind of investigation would be more appropriate resolution. But on the other hand, if we are looking at something like a more conventional rock, conventional sandstone, then probably a micropillar is a better way, because their grains and the pores are bigger than an unconventional, and micropillar scanning would be a better resolution for that. So this is showing how a scanning electron, now we are going into the scanning electron microscope, okay? And so this is the end frame we cut from the plug, and then to understand the heterogeneity within that plug, actually we further take multiple, at least 5 or 6 different measurements of XRF. It's a handheld machine. You don't need to pulverize the cuttings, or sorry, pulverize the sample. You can actually spot check the chemistry or the chemical composition of the rock at 5 or 6 different points, and then understand the heterogeneity. And on the basis of that, one can determine where to take the SEM spot. So SEM, if you see now, it's coming down to 1 millimeter scale. So it's a very small chip of the rock. Now you're doing some ion polish and all, and trying to look much deeper into the grain to pore, or the grain to grain relationship of the rock. Here also we are using a machine learning approach, because if you want to scan the whole thing using SEM, it's going to take quite a considerable amount of time. So by using a machine learning approach, actually different representative blocks within that SEM is identified, and then each of these blocks are analyzed and then upscale back to that 1 millimeter level. So, but a comparison of this was done by analyzing the whole 1 millimeter section by SEM, or 1 millimeter section by SEM to that of using the machine learning application method, where you identify only a few segments or sections and doing the analysis and upscaling. So that it was very comparable, very results were there. This machine learning approach was very useful actually to upscale the measurement of the porosities and other rock properties to at least to this level, and then from here to the plug level, and so on. So this SEM analysis can be done in a 2D space, and when you stack one over another, actually you can create a 3D image of that. So you will using what you call a 3D FIB SEM imaging technique to create those cubes, or where you can, for example, like if you are looking at a two-dimensional CT scan, that CT scan actually the pores maybe look even at times may even look isolated. They might look not interconnected. But when you actually do a 3D of that, and then you see that actually those pores are connected. So that kind of information are very helpful going from a 2D to 3D measurement. So here I'm showing a slide from an organic rich rocks, and you can see these are organic matters here, all these grays, and then all this other lighter color are the matrix component. For here, for example, here this is a pyrite. This is the rhomboidal pyrite colony here, and then you can see there's all these pores inside this in the organic matters. So this rock has pores inside the organic matter as well as pores inside the intergranular spaces, right? So two different scales are showing. This is a little bit a coarser scale of 10 nanometer per pixel versus 2.5 nanometer per pixel. Some of them actually, depending on how smaller the pores are, we may go even up to the 1 nanometer pixel as well. This has a big advantage in now understanding the different kind of pores those are there in your rock. Now, whether how many of these pores are organic hosted, or how many of these pores are intergranular spaces, now you can actually quantitatively know that and bring that information into your formation evaluation workflow, right? So all pores here now, I'm in the x-axis, you are seeing the radius, and then y-axis is the frequency. So you can see a distribution of the pore size for all the pores. And again, then PaOM is our porosity associated with organic matter. So how much of that pores are actually organic matter pores, or how much of them are intergranular pores? These informations are available. One important parameter here is the ATR. That is the how much of the organic pores are within the organic matter. So basically, in some of the organic matter, so suppose if you are less matured, that maybe those are not having that much of pore as compared to a more matured organic matter. So then the organic pores to the organic matter ratio is actually kind of a reflection of the vitrinite reflectance, or maybe you can compare that with a maturity of the organic rocks. So those kind of informations are deep, much greater insight of these of the rocks, particularly in the organic rich rocks, are very easily or understandable from digital rock analysis. So once these different rock types are identified, and then the porosities for all these different sections are estimated from or measured from here, from this digital rock, then those are actually converted using a lattice Boltzmann method for permeability. So now all these different rock types, you have different permeabilities, and then you can upscale back to your facies facies level from the whole core scale. Again, I was talking about the 2D versus the 3D. So once you have the 2D or you have the 3D, the SEM data, then actually you can go much more than just looking at the pores and understanding the porosity and permeability relationship. And generally, these porosity permeability relationships are different. Of course, it's based on different rock types. So comparatively between the two-dimensional versus the three-dimensional, the porosity and permeability relationship could be significantly different going from different rock types. Um, One of the major or the very important property in when we are estimating the saturation of the rock, mostly the petrophysicists use different saturation equations, and some of the common like the Archie's equations, the formation resistivity factor or the cementation exponent, or for that matter the saturation exponent are unknown. Most of the time people go with some common numbers that are known for a rock, or if it can be measured through a conventional core analysis as well, but it takes quite a significant amount of time in doing that. But these informations, that cementation exponent or the saturation exponent or the formation resistivity factors are actually doable um, from this resistivity, from the digital rock analysis as well. So now let's look into some relative permeability simulation method or application. So as I was saying, once you have that digital rock into your computer, you have the whole structure of the rock, the pores and the grains, and we are running a simulation here for two type of fluids, the oil and gas, and at different saturations. So in the x-axis, actually, you're seeing how they're, just different level of saturations, and you're seeing the relative permeability on the y-axis. So at different level, how these fluids are behaving in the presence of the other fluid, and that information or that simulation you can run using the digital rock analysis, and it's a great insight or great understanding on the fluid flow mechanism within the rocks that an reservoir engineer can generate and utilize quantitatively into his workflow. So when you have when you look into that, all these grains or the pore relationship, actually we come up with some kind of a spider plots where we actually defining the sorting, the grain size distribution, surface to volume ratio, coordination number, or elongation. So elongation means like how circular the grains or the pores are, that kind of information. So one thing you might notice that what is this coordination number, right? So coordination number, most of you will all know about the sorting, grain size distribution, surface to volume, and elongation. But coordination number is a new terminology that we are using here. The coordination number basically represents how many number of pore throats those are connecting the pore body. So a pore within the rock is the area where the fluid resides, right? But to get to that, how the fluids entering that or getting out of that depends on the pore throat. So the pore throats, if you have more number of pore throats, then you have a more easy or better deliverability of the rock as compared to if you are having just only one or two pore throats connecting to the pore. So that's a great understanding from digital rock, and we can. So here is a scenario where we are seeing two different petrotypes, and they are more or less similar, same range of porosities, and similar compositional properties, and etc. And when we are actually running this simulation, we saw that actually in the prototype 1, at different saturation levels or different wettabilities, the relative permeability of the fluids are not varying much as compared to the second type. And also, if you look at the drainage curve, the relative permeability of this one is much higher as compared to this one. So the only difference here, when you compare both these two the spider plots, you can see that here the coordination number is much higher as compared to this one. So that means that it has more pore throats connecting to this pore body. So as a result, it's having a much better deliverability as compared to this rock. So this information is very critical in understanding the flow zone behavior or of a rock, and it also helps directly into the or in understanding the deliverability of the reservoir. For a geologist, grain size distribution means a lot, the sorting, skewness, sphericity, roundness, etc. And we can get this information from our microcity measurement. You remember I was talking about the cutting a micropillar and then running a microcity on that. And actually from there, we can identify all these different grains. So once these grains are there, you can measure all the sphericity or roundness, or and make all those plots, understanding the skewness of those, and it gives a much better insight into now the depositional environment. So the geologist can use directly these informations in understanding the depositional parameter or depositional behaviors or the lithification of the rock, and actually decide on offsetting future wells in their reservoir. This is a slide just showing you how a micropillar is cut or a dimension, just to have a feel for it. So this is the end frame, and this is showing in the millimeters. So this is the scale. So we are looking at 4 millimeter sample here, and then this is how it has been, on the tip. Actually, this cut piece or the pillar of the rock is there, and then you run the microcity on that one. To get all those grain size distribution or the pore size distribution measurement out of that. It can go even smaller than that. It can go into a micrometer level as well. So one of the big applications, like I mentioned already, like from the grain size distribution, you can understand the depositional characteristics of the rock, and actually from there, you can have a very good understanding on the flow zone behavior, right? If you have a cubic kind of packing, very uniform grain size, it has a much better flow zone or flowing characteristics as compared to if you're a mixed sorted rock, where you have a grain size of varying size, or the pores are of varying size. So this is very helpful, right? So in summary, this when you're looking at the whole core, it is the CT scan of the whole core is been done. So whole core, when I'm talking about whole core, this could be a diameter of 4.5 inch core, or maybe different core companies have different diameters. So accordingly, you can CT scan them, but the vertical resolution we are talking about is about 0.3 millimeter. So that's the resolution we are looking at the rock, which is way beyond than a conventional logging measurement. A wireline log measuring density is probably around a foot or 1.5 foot in resolution. So by CT scan, actually, we are diving much more deeper into a much higher resolution and understanding or the heterogeneity of the rock and defining the different facies. And the next level, then we go into that much higher resolution. So that is your microcity or the SEM level. Like I mentioned, SEM, we are doing it more in the much tighter pores in the unconventionals, probably into the organic rich rocks, but in a more conventional kind of rocks, we are going for the microcity measurement. And then both these actually, using both this data, we can build those three-dimensional the digital rock within our computer, and we can run all those multiple different scenarios or the sensitivities for understanding the permeability or basically permeability, relative permeability, or sensitivity measurements, using varying your wettability, and all these simulations can be done. So till this point, now we are only talking about digital rock analysis, right? So that's not by itself is providing the whole answer. It's just giving you a much deeper insight into the rock, understanding how the rocks is, the pores and the grains are disposed, or how they're going to behave with the fluid and etc. But we need to integrate that information to the whole reservoir characteristic workflow, right? So when people working in the reservoir characterization group, they use data from multiple disciplines, whether it could be from geology, from petrophysics, geomechanics, and reservoir engineer. And the sources could be different as well, like the logs, the fluids, the rocks. When I'm talking about the rocks, I'm talking about the cuttings or the sidewall core or a whole core using the digital versus, as well as the conventional core analysis. You have to remember one thing here, that digital rock analysis is not disruptive. It's not a disruptive technology or disruptive the conventional core analysis. Conventional core analysis has its own importance and significance, and digital rock is just complementing that and getting into a much deeper insight and reducing the uncertainties more uh, um, in coming up with a much better answer or in reservoir characterization. So when you look at this multi-scale data information, so you go first we start up with the seismic, at a much bigger scale where you in the basin level, or you identify where your well locations could be, or understanding the much bigger structure. And then you go to the well level, and at the well level you are acquiring data for using either wireline log or from the whole core. So that is in the meters and feet in that level. So then from there you go and extract plugs and go much deeper understanding into the plugs. So the plugs are in the range of in the inches or inches or centimeters scale. And from there now you're diving much deeper into at a higher resolution scale, going into micrometer or nanometer level. So as you go deeper, more and more highly focused resolution, you may lose context going into from here to the very fine high resolution rocks, right? A high resolution scale. So you may lose even context of the whole thing. So, but how you getting back, or how you integrate all these information and upscale that information to the log level, or or better basin level understanding from correlation from well to well, is the workflow that we are talking about. So that's how it's become an integral component within the digital rock. With that multi-scale, going deeper is we interrogate at multiple different level, and coming back we integrate all that information back to our um, much larger usable scale in understanding the entire basin. Um, so I'm going to talk about a little bit on how these integrations are done. I'll give you a couple of examples here. Um, so here, these are some of the the four ways actually those where we generally integrate this information. The first one is, of course, that we're talking about the core plugs and using either and the CT scan or the SEM data. One of the things that we have not touched upon is the NMR technology. The core, the NMR can be run in the well, can be a part of the wireline program, or also we can do the plug level NMR within, or the cuttings NMR in our lab as well. So that's called a benchtop NMR. So that brings in a lot of understanding as well, because NMR talks about the fluid and the pores, pore size distribution. So that's, you see, it's already complementing the SEM or the microcity level of discussion, and how you actually that together provide you a much deeper understanding of the rock and the fluid rock and the fluid of the reservoirs. And then the next level is using some machine learning applications, how you upscale that information, and then combine that with conventional the physical core analysis data. For example, like XRD, XRF, those are done using the conventional method, or understanding the organics, the geochemistry of the organics, etc., or the geomechanics, and then combine that with these informations, and then finally integrate that to the log level, or with the wireline log measurement. So that gives you a very robust model of the reservoir, um, for not only for the geologists or petrophysicists, but also for the reservoir engineers. This is one example of showing how NMR and SEM were integrated in understanding an organic rich rocks in North America. Here the wireline log is in the middle, and this plug is your benchtop NMR. Both these measurements are different, right? I mean, even though both are NMR, this one is a gradient field magnetic NMR, and here you are a non-gradient magnetic field, and it's a higher frequency as well. So in organic rich rocks now, with the more advancement of the actually NMR wireline NMR tool, only very recently we are being able to partition those early signals into understanding the organic rich pores, or how they're behaving. Before it was not even possible. So now still we are seeing them based on those early signals as well as the T1, T2 ratios. You can see or identify those organic pores, but these organic pores, the size of those pores, are not necessarily all of them are organic pores. A lot of them are actually intergranular pores, which are probably of the similar size. So that understanding now we can further subdivide into organic versus the inorganic pores using the benchtop NMR, and that has been complemented by SEM, looking into that or understanding or segmenting the pores into organic versus inorganic pores. On another note, also NMR gives a much better understanding of the clay-bound pore size pores, so which actually the SEM cannot see. So when your SEM is looking at an effective, visual effective porosity, so it cannot see the clay-bound size pores, which we can get the signal from the actually wireline NMR or a plug NMR measurement, and then we can combine that to come up with a total porosity measurement from SEM. So by integrating these NMR and SEM, now we can actually get into a point where we can segment our producible the pores, producible the porosity. What I mean by that is that we now subdivide these or segment these pores into organic hosted versus inorganic hosted, etc. So the intergranular versus the organic pores, that classifications we can do. This has pretty significant importance in understanding the decline curve analysis when you're looking into the production profile of a well. That's beyond the scope of this presentation, but I'm just mentioning here that with this segmentation of the producible pore on the porosity, it gives a much deeper insight in understanding that application. There's another integrated approach here, comparing. You remember I was talking about the CT scan for the whole core. So it's a CT scan from the CT properties are a function of a density and the P measurement, lithology indicator, and these radial images, we can open it up and actually compare to a wireline resistivity image. So wireline resistivity image or an acoustic image are already pretty high resolution, but when you're talking about CT level of resolution, it's much coarser. So when we combine both these two, and we actually get much more information in understanding the fractures or how all the other rock features within that, because CT is giving you a much higher resolution information. So it's combined, both these actually helps the geologist to describe the rock or understanding the facies or the heterogeneity in a much better way. One other application I'm going to talk about is the how we characterize the horizontal well, particularly in the North America North American context, where we are having quite a significant amount of unconventional drilling going on. And reservoir properties, we know that they vary quite significantly. But running a full suite of LWD log or doing a wireline log into the horizontal well occasionally are very expensive, and it's not doing well for the economics of the well, or or production. So how you combine multiple informations and coming up with a good characteristics of the reservoir properties along the horizontal is very important. So accordingly, then you can actually design the completion as well, because during reservoir stimulation processes are pretty expensive, and if it's not done well or it's not been optimized, a lot of these investments actually may not give any returns at all. So it has to be optimized, and one of the optimization method is actually we are using the cuttings here, right? So here is a workflow it's showing here. Is first is a projection of vertical well data onto the horizontal well bore. So if you have a suite of log into the vertical well and analyze that, and then you can actually, using the geosteering application, project it onto the horizontal well bore. So it will just be a projection or transposition of the vertical to the horizontal. It will not be able to capture the lateral variation or the lateral heterogeneity that's there in the rocks. So for that, you can either run a pulse neutron log to capture that, and to complement that, actually, you can either, or you can do, one can do the cuttings analysis, and further constrain the model, or or define the model for understanding the mineralogical changes or the porosities, etc. So doing a SCM level of investigation could be pretty expensive and time consuming as well. But when you combine this workflow from projecting the rock, vertical into the horizontal, and then the cuttings, using the cuttings, you can actually, one can define the mineralogy from the XRD, XRF, and then from that, you can identify a few cuttings which we want to go much more deeper, looking at the SEM level. So not necessarily you do an SEM for the whole entire segment, or all the cuttings, or entire the wellbore, but you can actually narrow it down to a few samples which you can utilize to go a little bit deeper doing the SEM kind of understanding, because SEM provides you the segmented pore informations, organic matters, etc. So, and with that, you can actually now define or characterize the entire horizontal wellbore in a much better way, and accordingly, in a more intelligent way, you can design your stimulation design. So I think with that, I think I'm coming to an end to my presentation. I believe the stage is open for any questions if you may have. Nikhil?
Yes, sir. Yes, sir.